quickly, we're going to go through ionic substances. I'm not going to dawdle on ionic substances. This may be a little bit confusing at times, so please don't stress. That's why I just want to sort of quickly brush over it. I don't expect any of you to fully understand ionic substances after this. So ionic substances are essentially where you have a positive ion and you have a negative ion and they join together. So in this case here, you have chloride, and you have sodium. So table salt. Table salt is an ionic substance. It's got sodium and it's got chloride and they join together like this. And essentially what happens is the cations and ions combine to form a 3D lattice. So these join by just attractive forces. These join because there's a negative and a positive charge and then just attracted together. The 3D lattice is held strongly by electrostatic attractions. And for example, NaCl, as you can see there, every sodium is surrounded by 6 chloride ions. Ionic substances. So these are the properties. They have a really high melting point. They're not very malleable. They're quite brittle. So what that means is if I were to hit them, what would happen is, if I go back, what happens if I hit this is instead of having the electrons to move in between and allow for these molecules to sort of squish up together, what happens is there's nothing moving around. So what happens is this whole layer shifts. The whole layer shifts. And then what happens is these two end up on top of each other. These two end up on top of each other. These two end up on top of each other. So what you end up with is positive and negative charges next to each other. And that's not good. They're going to repel. And so what happens in that split second is they repel each other and it shatters. And that's what we refer to as brittle. So strength, they're fairly strong. This is determined by what we call a scratch test. So all ionic substances can go through a scratch test, and they can withstand a relatively high amount of force without being scratched. And then conductivity, so in liquid state, they can conduct, because when they're in a liquid state, if you think about it, this lattice is broken apart, these ions are free moving around, so they can carry charge. When they're in a solid state, these ions cannot move out of this lattice, so they cannot conduct. That's about it. So there's some key molecules that you need to know, or some key formulas you need to know. They're all within these tables here. So you need to know, if you were told, create a molecule that is potassium, let's say potassium hydroxide. So you need to know what hydroxide is. You need to know what potassium is. Now, what's really important here is I've highlighted in yellow the key ones I think you really need to memorize. I think cations wise, you should know nearly all of these, to be honest. Maybe not these ones here, not the ones with 2 in them or the ones with 3 in them. But I would also argue that, and copper 1 you should probably know, and copper 2 you probably should know. But the rest of them, I would argue you don't need to know these ones, but you do need to know all the other ones, especially the ones highlighted in yellow, but like lithium, sodium, potassium, calcium, barium, zinc, magnesium, you should really know these ones as well. So these are all the ones that you should know. These are just the cation forms of these, so these are the ion forms of these molecules. And then for negative ones, I've highlighted the ones in negative I think you need to know. There are a few more I think you probably should know as well, like chloride. I also think like, which one was it as well? Iodine and bromide and fluoride. They're all down there, sorry. These 4 as well, I also think you should know. And I always tell my classes, you should know this one as well. And probably nitrite, although nitrate is slightly more important. But the other ones here are less important. I don't think you really need to know these ones that are not highlighted. You just need to know these ones that are highlighted, plus probably these extra 5 ones here. So these are things that you do need to commit to memory. But please don't worry about going out there and creating flashcards and sitting there and memorizing these things and spending lots of time. It comes with time, you will see them all the time. You will be utilizing these all the time. You'll be going through them all the time. So please don't stress about sitting there and going, I really need to learn them right now. You can spend a little bit of time and wait, because as you go through lots of practice questions, as you go through different topics, you'll see these all the time. They kind of just end up being committed to memory. So yeah. And then sort of lastly is solubility with ionic substances. So with solubility, what's really important is that we know the definitions here. So you know what dissolving and dissolution means, what a solution is, what a solute is, what a solvent is, what an aqueous solution is. Solubility is essentially where ionic substances are put in there and whether they dissolve or not. So if you put salt in water, does it dissolve? Generally, it can, but it doesn't necessarily do that. And then there are some other things that if you put in water, it may dissolve, it may not. It's just whether things dissolve or not in water. And then polarity, we've kind of already discussed this very quickly, but remember that polar molecules have that slightly positive and slightly negative charge. Non-polar molecules don't have that. What's really important is that polar molecules dissolve. Now, why do polar molecules more likely to dissolve? Because they're attracted to water, whereas non-polar molecules won't dissolve in water because they're not attracted to water. Because like things are attracted when it comes to polarity. So when we talked about charge, it's the opposite. When we talk about polarity, it's the same. Same things are attracted. So polar molecules are attracted to polar solvents. Water is a polar solvent. Non-polar molecules are attracted to non-polar solvents, such as oils, but they're not attracted to water. So really important to understand that there. So when ionic substances dissolve, they dissociate. The ionic lattice is essentially attacked by the water molecules, by the positive hydrogen ends, and then you get the negative oxygens. And the ion dipole attraction is so strong that the lattice breaks apart and the ions become surrounded by water molecules. They become hydrated. NaCl, NaOH, these molecules all dissolve this way. So if you think about it, this is essentially what happens. You have a solid, you put it in water, and then you end up with these two ions. And then is something soluble or not? So there's this rule that we refer to as the Snape rule. Now, the Snape rule essentially says that any molecule or any ionic substance that contains these will be soluble. That means it will become aqueous, it will break down, and it will dissolve in water. So anything that has these five molecules will have, or these five sort of little compounds as a part of it, these will dissolve in water. So this is the Snape rule, and it's something you need to know. It doesn't necessarily mean anything that doesn't have them won't dissolve, but anything that will have these will dissolve no matter what. So then we look at precipitation reactions. So precipitation reactions are where we combine two ionic substances, and when we combine two ionic substances, they're probably going to react, and they do react, and they switch. So the sodium will switch and join with the nitrate here, and the chloride will switch and join with the lead here. So we're going to get a little bit of a switch. So we get PbCl, as you can see here, and we get NaNO3. Now, we're going to talk about states in 1 second. I shall grab up states now because I think states are important. We have these 4 states. So, we have these 4 major states. And what I refer to by states is what is the molecule, or what is the compound, what form is it in? So we have solid, we have liquid, we have aqueous, and we have gas. Solid means, as it sounds, a solid mass. It's going to be a solid. If it's in water and it's solid, that means it hasn't dissolved. That means it's a precipitate. If it's just a solid generally, like a metal, it's just a solid. Then we have liquid. Now, liquid is important. Liquid is only for water and then only for pure chemicals. So if it tells you that a chemical is pure, so we have pure ethanol, or we have pure something, that is a liquid. And it's really important that you know and that you are told that it is pure. If you are not told it is pure, you assume it is aqueous, which means it's a chemical that has a bit of water in it. So it's like we've dissolved salt or our sodium chloride into water. We call it aqueous because it's now in a liquid form, but it's not pure because it's got water around it. So we call that aqueous. So aqueous assumes that the chemical has been diluted with water, which 99% of them are, and has a concentration. So water is never ever in aqueous form for VCE. Water is always a liquid, by the way. And then gas, as it says, it is a gas in the air, like it's just a gas. So they're the 4 states. So it's really important you understand the 4 states. Now, jumping back to a precipitation reaction is where we put 2 aqueous forms of ionic substances and we put them together, and then all of a sudden you get this solid forming, because PbCl2 is actually what we refer to as a precipitant. What this means is that the bonds formed between Pb and Cl are stronger than the water's ability to break it down. So when these things break apart and then join together in these 2 molecules here, these 2 compounds here, PbCl2 will be able to hold itself together as a solid. NaNO3 won't. Nor can NaCl, nor can PbNO3 too. None of these molecules can hold themselves together. Water is stronger. However, PbCl actually is stronger, and therefore you get solids forming. And that is what we refer to as a precipitation reaction, where we have aqueous, 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 but we have one solid that is formed, and that is the precipitant. Now, in the last slide, we went over a precipitate forming, but what's really important is that there is a precipitation reaction. You may be asked to write out an ionic equation. And so what's different about an ionic equation is this here. I've kind of got this all out of order, I apologize. Is this here. You're given this here. This is a precipitation reaction. You're told, all right, what about the ions? What's happening to the individual ions? So if you look at the individual ions, these are all ions, because you can break these all apart. These are all broken down in water. But then on the other end, you only have 2 ions left, and you've got AgCl as a solid. These are no longer an ion because they're a solid. So what is my net ionic equation? And this is what you'll be asked to write out. You'll be asked to write out, what is your ionic equation? What is your net ionic equation is the other wording for it. This is what your ionic equation is. It's what has changed. You only put in the equation what has changed from one side to the other. So what has changed? This NO3 negative and this NO3 negative have not changed. This Na plus and this Na plus have not changed. They're the exact same. So get rid of them. Go, 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 and go. So you're only left with these, because this Ag plus has changed. It's now in a solid. This Cl minus has changed. It's now an AgCl. So this is a net ionic equation, and it's quite important to understand that that is what an ionic equation is asking you to do. So that is essentially what an ionic equation is, and that is what we're looking at. Now, skipping over that one because we've kind of already been over that. I've kind of jumped through and done a bit. The only other thing I want to talk about quickly is with a chemical reaction, we also sometimes like to balance things. And what that means is we like to have the same amount of electrons on the left as we have on the right. So if we look at this here, we want to combine the following ions. We want to combine copper 3 and we want to combine phosphate. So we've got a copper 3 and we've got a phosphate. We combine them because of the plus 3 and the negative 3 we've had to do. That's actually meant to be negative 2. Sorry, I don't know why. No, that's meant to be negative 2. Why have we got copper 3? This slide is slightly wrong. Apologies. That will be my bad. That'll be a typo. So what we're actually working with here is, if I scribble this out, this is actually 2 plus, and then the other one is 3 minus. That's correct. So when we look at these charges, that's what I meant. When we look at these charges, we've got 2 plus and we've got 3 minus. If we join them together as is, we end up with a charge of -1. And we don't want that. We want to be neutral. We want to be 0. So what I have to do is double this, make this -6. And you'd think, well, that'll make it -4. So that's silly. But then I need to multiply this by 3. And if I multiply this by 3, I then get +6. And it's the first sort of factor that's the same. So now these cancel out. So if you see here, I've got 3 and I've got 2. As I said here, I multiply this by 2 and I multiply this one by 3. So I've got 3 and I've got 2. So this is my equation. I've gone from this and this to this. But this is not balanced. Why is that? Because I've got 3 of this. I've got 2 of this and I've got 8 of this, because 2 times that, 2 times that. I've only got 4 of this, I've only got 1 of this, and I've only got 1 of this. So this is wrong. So I need to balance it. So To balance it, I need to put numbers out the front. So in balancing this equation here, I've gone and put a 3 in front of the Cu3 plus, I put a 2 in front of the PO3 minus 4, and I've put a nothing there because I didn't need to do anything on this side here. So essentially this 2 is referring to double this, and this 3 is referring to 3 times this. So I have 3 of this here, I have 2 of this, and I have 8 of this now, which matches up the other side. So that's what balancing is. Then we discuss states, and then as you can see, you bring it all together in an ionic equation. So this is your precipitation reaction. As you can see here, you go to a solid. Here, you go to your net ionic. Now in this one here, there's no balancing. There's no balancing necessary because as you see, we have 1 silver, we end up with 1 silver. We have 1 chlorine, we end up with 1 chlorine. We have 1 nitrate, we have 1 nitrate, and we have 1 sodium ion, we have 1 sodium ion. So there's no need to balance this equation here, which is really, really important. So there's a couple of practice questions here, but I felt what we should do is I reckon we'll go through this one here. So what I'm going to do is I'm going to sort of give you all a minute or two to have a go at this. What's really important here is that there is a precipitate that is formed. So we have lead nitrate, which I will give to you. So lead nitrate is PbNO3. I can't draw, so it's not really working. Plus potassium. And we have Ki. These are both in aqueous form. Aqueous and aqueous. So these are both in aqueous form. And then what's most important is what about if we need to make sure that we have the right charges. So let's go all the way back. And I'm happy for all of you to do this if you've got access to the slides. If you don't, then take a quick screenshot. We need to access this. So where is our iodine? Iodine's down here. What was our other one? Lead nitrate. So nitrate, NO3 negative. Then we need to go back. We need to go, all right, what was potassium? Potassium was K positive. And then what was the other one? It was lead. So lead, it'll be lead 2 plus, lead 2 because lead 2 is the only option on here. So we have lead 2 plus. So now we need to go back. We jump all the way through. Apologies. All these animations. So jump back through and we go, all right, well, this was 2 plus, this was -1. So this one needs to be 2. Now from here, I want all of you, and don't worry about the net ionic for now. I want everyone to have a go at the molecular equation right now. So what will go on the other side? What are the 2 things that are going to go here and here? Have a think. Just take a minute, write it down if you want, and write down what you think is going to be going on here. And if necessary, balance this equation out. So when you're done, balance it out. And I'm telling you now, there is a precipitate that forms. One of them is a precipitate. Which one do you think it is? All right, I'll give everyone another 30 seconds or so. All right, let's go through and do this one now. So we have PB, which was 2 plus, and we have ion, which is -1, so that's now going to be 2. We then also have K, or potassium, nitrate, which is +1, -1, so that's just going to be nothing else on there. Now, what's really important is we think back to our Snape rule. What was the N in Snape? The N was nitrate, so this has to be aqueous. Oh, that was terrible. That's meant to be a bracket there. It looks like an L. So this has to be aqueous because this nitrate was part of the Snape rule. So as I said, one of these have to be a precipitant. So this one has to be the precipitate. This has to be the solid. So that one there is going to end up being the solid. Now, I would think I'm done here, but I'm actually not. I need to balance. I've got PbNO3 with a 2 at the end of the NO. I only have 1 here, so I'm going to need a 2 here. I now have 2 potassiums, so I need to put a 2 here. I now have 2 iodines, but I also have 2 iodines here, so I'm happy with that. So I'm now all balanced. I needed to put a 2 and a 2, and that's how you balanced out that equation. Now, really importantly, if I were to do the net ionic equation here, I would have done Pb2 plus, and that would have been aqueous. This looks terrible, I apologize because of my using the keypad. And this would have been I negative, also would have been aqueous down here, and it would have gone to PbI2, and this would have been solid down here. And really importantly, you still need to balance out this equation, so there would be a 2 here as well. And this would be aqueous, aqueous, solid. And that is what my net ionic equation would have been for this one here as well.